Section 5.4 works to teach you molar mass and conversions. So to begin with, molar mass can be used as a conversion factor. Remember, a conversion factor is something that just equals 1, so it equals unity. And it's used by a conversion factor, meaning it's used to convert one entity into another. So meaning if you go weigh out 1 mole of carbon on a balance, it's going to weigh 12.017 grams. Now it doesn't matter if you've got moles in the denominator or in the numerator. It just depends on what it is that you're trying to convert and what are you trying to convert it into. So there will be a correct way to do it, but you could write it either way. And so as you're looking at all these conversion factors, note that that's just all they are. They're written as 1 mole of carbon over the mass of that molecule or that atom. So the first three, these are all elements. So these are molar masses of the elements, where you just write 1 mole over the mass of that element. And this down here is sugar. So you've got 1 mole of that sugar over the mass of that molecule. And now notice on each of these things, it's always 1 mole, 1 mole, 1 mole, 1 mole. And that's because 1 mole weighs the amount you see on the periodic table. But that there's always going to be different masses. So 342, notice how bigger, how much larger the quantity of sugar it is that it takes to achieve the same mass as carbon. So represented here is supposed to be just 1 mole. And so that's why 342 grams of sugar, but carbon, you only need 12 grams of it to have the same number of molecules or atoms as each other. So in each case, there are 6.022 times 10 to the 23rd molecules or atoms represented in each one of these dishes or in the balloon itself. So these are molar mass entities, and they can be used as a conversion factor. Now the balanced chemical equation can also be used as a conversion factor. Remember when we looked at transitioning from 3 volumes of hydrogen to 2 volumes of ammonia? And so when we did this, we set it up as a conversion factor. Or we might have said 3 liters of hydrogen to 1 liters of nitrogen, and so on and so forth. You can do that same thing, but now instead of writing liters, you can replace that with the word mole. Because all we're doing is saying, hey, for every 3 hydrogens, we should have 1 nitrogen. And for every 1 nitrogen, you should have 2 ammonias. And so that's all we're trying to work on, is how can we use the chemical equation to be written like a conversion factor. And note, once again, it doesn't matter what's on top, what's on bottom. That is going to be decided based on what you're converting from and what you're going to be converted to. But each of these entities still stands. Okay? We can write all of the conversion factors for this one chemical equation can be written like any of these things, where we're combining hydrogen to nitrogen or nitrogen to hydrogen. But notice what goes in front of moles is always, always, always the coefficient. And I know this can sometimes be confusing for students, because before on the previous slide I said 1 mole, 1 mole, 1 mole. It's always 1 mole. And that's because you're saying 1 mole has the mass that's on the periodic table. Here I'm saying I'm using the chemical equation, not the periodic table, the chemical equation to be my conversion factor. And in this case, the number that's in front of mole is always the coefficient from the balanced chemical equation. The chemical equation does have to be balanced first, or none of these conversions will be correct. Alright, so now we know that they can both be conversion factors. How do we use them? How do we allow the chemical equation or the molar mass, how do we let those convert from one entity to another? And so in this case, I think we like to let the units be our guide. And I'll kind of explain what I mean by that as we go along, and I think it'll become more clear. But let's say you want to go from mass in grams of some compound, and we want to convert it all the way to submass in grams of another compound. We can't just go from grams to grams. We have to go through moles. Now we could use mass percent, but it's easier, I think, sometimes for students to wrap their minds around the idea of using moles to convert from one to the other. So when we do this, notice we've got the 2 types of conversion factors here. We have our molar mass conversion factors, where it's always 1 mole per number from the periodic table, okay, or number of grams, which are from the periodic table, or over 1, or you've got this coefficients from your balanced chemical equation, that second type of conversion factor I mentioned. And in this case, this blue number is always a coefficient from the balanced chemical equation. So let's see how this looks. Let's say we have this equation here. Carbon plus oxygen yields carbon dioxide. if we start out with 5 grams of carbon, we can first convert from grams of carbon, where in this case, grams of carbon is the same thing as that mass of A. A is just standing for C for carbon in this case. We're converting from grams of carbon to moles of carbon. And to do that, we use the molar mass, so that 12.011 grams. Okay, this converts grams into moles because the grams on the bottom will cancel out. Now we've got moles of carbon. So now we want to go from moles of one entity to moles of another entity. And in this case, the question might have asked us for grams in oxygen. And so in order to go from moles of one substance to moles of another substance, this is where we have to use our balanced chemical equation, where we say moles of A, in this case, moles of our carbon. We put that on the bottom because we had moles on top originally. We want them to cancel. Then we're converting it into moles of oxygen. And now to notice there's a 1 in front of each of these. That's not just because it's the 1 like over here, but instead it's 1 because that is the coefficient in front of the element or the molecule in the balanced chemical equation. And now that would convert it to moles of oxygen. And now I need to go to grams of oxygen. So to do that, I use my molar mass. 1 mole of oxygen is equal to 32 grams of oxygen. Now remember, we can't just look up oxygen on the periodic table. We have to remember oxygen has a 2 as a subscript. So 16 times 2 gives us 32, where 16 was taken from the periodic table. And that means that our moles of oxygen cancel and our grams of oxygen get carried through to the answer. Then how do we get our number? The number, in my opinion, isn't as important because you're going to get there if you do the math right. Setting this up is typically the hardest part. But once you set this up properly, then it's just a matter of typing in the numbers into your calculator. I type in 5 times 32 divided by 12. Okay, don't feel bad about hitting enter a bunch because you could type in 5 times 32, enter, divided by 12, and you get the right answer. Okay, sometimes it matters parentheses, etc. Alright, so from here, remember, you want to just relate this back in your mind to this letting the units be your guide. We're going to want to do this strategy for all of the examples that we have in this lecture video. Alright, but one thing I want to mention, after this video, I do want you to go complete the lab number 9 activity. What it is I set up some puzzle pieces that you're literally going to cut out, and then I recommend putting like some tape, some clear Scotch tape over the boxes and the puzzle pieces, and then just writing on it with a dry erase marker. Why I think this will help you is these puzzle pieces only fit together in certain ways, and so I hope this will teach you what you're looking for when you're converting from one entity to another. So after this video, go complete that lab activity. Alright, so here's our first question. We know hydrogen sulfide, which is a gas that smells like rotten eggs. It burns in air to produce sulfur dioxide and water according to this equation. So my question to you is this. If you react 4.5 grams of hydrogen sulfide with excess oxygen, and we only say that just to make the equation easier, how much water is produced? Okay, so the excess oxygen, just ignore it. Okay, so in this case, we're wanting to react 4.5 grams of hydrogen sulfide with excess oxygen. So in our conversions, we're going to start out with 4.5 grams of hydrogen, and we're going to let it be producing water way over here. And that is our strategy. Alright, so first off, let's fill in these boxes. The first thing you have is mass of hydrogen sulfide. That's our first substance. And we're going to convert that into what comes next. If we go number of grams of A, which is hydrogen sulfide, to moles of A, which is moles of hydrogen sulfide, we're going to end up with moles of hydrogen sulfide on the top. And then if we go from moles of hydrogen sulfide, using the balanced chemical equation, we can make it to moles of water. Then we can go from moles of water using the molar mass off the periodic table for water. We can convert from moles of water to mass of water in grams. So what this looks like, the conversion factor that you will use here is grams of hydrogen sulfide per mole. And remember, this grams that you see here is just sulfur's mass plus hydrogens plus hydrogens. Then we use our balanced chemical equation. So Moles of hydrogen sulfide is going to be on the bottom, so it'll cancel. The 2 goes here. The 2 for water comes here. And now we convert our last conversion factor. We've got going from moles of water, cancel the moles of water, molar mass of water on the top. That is our game plan. So let's see how this works. Does everything cancel? Grams of hydrogen sulfide cancels, moles of hydrogen sulfide cancel, moles of water cancels, and grams of water is going to be our units for our final answer. Now make sure you know where these numbers are coming from. So 4.5 was given in the problem. 34 grams per mole is the weight of hydrogen sulfide. Remember, molar masses always go with 1 mole. 18 grams is the molar mass of water, and it always goes with 1 mole. These two 2's are coming from hydrogen sulfide's coefficient and water's coefficient. And that's going to give us 22.4 grams if you multiply across. So I would have typed in 4.5 times 2 times 18.01, enter, divide by 34.1, enter, divide by 2, enter, and that gives me 2.4 grams. Alright, let's try another one. This case, we're reacting 6.8 grams of oxygen with excess hydrogen sulfide. How much water is produced in this case? So once again, set up your conversion factors, but this time we're going from mass of oxygen to mass of water. So I changed what I had in each of these 2 boxes. Now I need to go from mass of oxygen to moles, molar mass, moles of oxygen to moles of water, balanced chemical equation. Moles of water, grams of water, we're going to go with the molar mass of water. So then when we put it in this, we always check, did it work out for our units? Grams of oxygen got canceled. Moles of oxygen cancel out. Moles of water cancel. Grams of water is our product. And then we do the math and get 2.6 grams. Let's try another one. This time we're going to start out with 9.1 grams of butane. With excess oxygen, how much carbon dioxide is formed? So in this case, it's the same process, just our names have changed. So mass of A, that is what we're starting out with, 9.1 grams of butane. What is next? We need to convert from grams of butane to moles of butane, which means our next conversion factor should have grams of butane in the denominator, moles of butane in the numerator. The number that goes here is the mass of 4 carbons plus 10 hydrogens. That will allow us to convert to moles. So we need to convert from butane to carbon dioxide. So if moles of butane was a numerator, we need to put it in our conversion factor as a denominator, and these coefficients need to be in our conversion factor. And now we're in moles of carbon dioxide, and let's convert to grams of carbon dioxide. So now you're going to use this molar mass conversion factor, where moles of your carbon dioxide are on the bottom, 1 of them, and the number from the periodic table goes above it, where it's carbon plus 2 oxygens, to give you a total mass of 44.01. Now you check your units and see if they cancel. This is where it makes and it really helps if you write neatly and write grams of, moles of. Don't abbreviate moles with an M. M stands for mass. Make sure you write stuff out, show how they work, make sure that what you end up with is what you're trying to end up with, and then you do the math. Alright, work through this slowly. Maybe try to do this problem again on your own, but with a different number and without looking. Or maybe try convert from butane to water or oxygen to water. All of these problems are done the similar ways. It's just letting the units guide you to reproduce the correct answer. Now go complete now lab number 9 and then read section 5.5.